All right, I'm going to work through a few of these colligative property problems, and then I'm going to do the stoichiometry. So if you don't need the colligative property problems, then just fast forward. This is not for my regular chemistry. You do not need to worry about these. All right, the second problem for colligative properties is pretty similar to the first one, but I'm just dealing with my freezing point instead. So my solute is magnesium bromide. So my I would be equal to 2. There's my KF. My solvent is acetic acid. So what I do not have is my little m. I need that. And I don't even have moles, so I'm going to have to use my molar mass again. So I have 35 grams of magnesium bromide. (184.11 grams per 1 mole. Gives me 0.190 moles of my magnesium bromide. So that's moles of solute. Need to divide that by kilograms for my solution. So I need to move my decimal back 3 places to be 0.4000 kilograms. Top number divided by my bottom number and keeping it at 3 sig figs because of my moles. I end up with 0.475 molal, little m. So now I have everything I need. So I need to find my change is going to be my KF, which was given to me. My molality, which I figured. And then I said my I was 2, but it actually should be 3. I'm sorry. 2 bromine and 1 magnesium. So my I should be 3. Multiply is going to be 5.56. Once again, 3 sig figs because of my points. 475. 3 is a counting number and 3.90 is a constant. So those do not become part of the sig fig process. So that's how much the change was, and I'm dealing with freezing point. So I look up on my chart for acetic acid. The freezing point is 6.6 degrees Celsius, and it depressed by 5.56 degrees Celsius. So that gives me a new freezing point. Well, I'm sorry, this wasn't 6.6. This was 16.6. I have trouble reading my own writing. 16.6 came from the chart at the top of the page. Original freezing point minus 5.56 degrees Celsius would give me 11.04 degrees Celsius. That would be my new freezing point. All right, on the next one, a benzene solution, and I already have, so if it's a solution, that is the new boiling point and the new freezing point. So if I look at benzene on my chart above, I see that originally it boiled at 80.1 degrees Celsius, and its original freezing point was, looking at my chart, 5.48 degrees Celsius. So like I said in class with the notes, my delta, my change is always a positive number because it's just how much is changing. Kind of think about how much it would be changing like on a ruler or a number one. So delta T of boiling is going to be equal to the absolute value because I want it to be a positive number of 87.3 minus 80.1 and that gives me 7.2 degrees Celsius. So that means it increased by 7.2 degrees. Same thing with my freezing. Now freezing, it can be a little bit harder to understand because once again, it's how much it changed. So I need to take the absolute value of my higher number, which would be my original, and subtract the new freezing point, which in this case is negative 1.12. So negative and negative makes a positive number, so it actually becomes 5.48 plus 1.12, so 6.60 degrees Celsius is how much that changed. All right, and then the last one. "50 grams of a molecular solute." So if it's a molecular, that's a covalent compound, so that tells me I is equal to 1, or dissolved in 600 grams of nitrobenzene. So that's my solvent. And the boiling point of the solution is 214 degrees Celsius. Find the molar mass, and molar mass is always grams per mole. I have the grams. I need to find how many moles I have. So what relates to that is my little m. Okay, so I have my original boiling point and I have my new boiling point. So I can find out what my delta T of boiling is. So I'm going to take the absolute value of 214 degrees Celsius minus 210.88 degrees Celsius. And that gives us 3.12 degrees Celsius. That's how much the temperature changed. So now if I set my problem up, I know the change, so I'll say 3.12 degrees Celsius is equal to, we're dealing with boiling point, so my KB, which is given to me, 5.24 times my little m times my I, and since it was a molecular compound, that was just 1. So when I do my math, divide by 5.24 times 1, I get that my little m is equal to 0.595 molal. All right, so that's what I have now. So now we go back to our lessons earlier with molal. I know my molality. I don't know how much solute I have. That's what I'm interested in. I know that I have 600 grams of my solution. So that becomes 0.6000 kilograms because it has to be in kilograms. So bring this up and I multiply them. So I get my X is equal to 0.357 moles, which was what I was after. So I want to find my molar mass, and we said to find our molar mass, we always do grams per mole. So in this case, I had 50 grams divided by how many moles. I calculated 0.357 moles, and I end up with 140 with a decimal for 3 sig figs grams per mole. So that's a pretty good problem. Pretty good problem. May see one like that on the test on Friday. All right, so that kind of conquers the problems we didn't have time to get to in class. So I'm going to move back now a little bit for stoichiometry. So let me move my notes back. So we're going to talk about solution stoichiometry. Is basically the same as regular stoichiometry, except you need to remember the following. Since molarity is mole per liter, so you can almost think of it like a conversion factor. If I say something is 3 molar, then that's the same thing as saying that it has 3 moles per liter of solution. So once I set those numbers like that, one on the over the other, you can think how it could possibly fit into a stoichiometry problem. But just to kind of shorthand that a little bit, if I know the molarity and I know my volume, how much I have of that solution, and I can multiply those numbers, and that will give me moles of solute. Because if you think about it, if I know liters of solution and I know the molarity, which is moles per liter, then if I multiply those numbers, my liters cancel out, and that will tell me how many moles of solute I have. And then once I know how many moles of solute I have, it makes sense to put it in a stoichiometry problem where I have a balanced equation, because then I can use my mole to mole ratio. Then if we want it to work backwards, if I already know my moles of solute, I would divide by the molarity, and that would equal my volume of solution. So if you think about that, 1 moles of solute was my given. So I would multiply that by the molarity, which is moles of solute per liter of solution. And same thing, then once I had liters of solution, then that may be what I needed to get to in the answer of my problem. So let's look at a couple of these. We're not having a separate quiz over these, and there may possibly be one or so on the test, but not a whole lot. All right, I have my nice balanced equation. It says how many grams of silver, silver is a solid, would be formed by the reaction of excess copper. When something is in excess, and that just tells me it's not going to be a limiting reactant problem, with 208 mils of a 0.1 molar silver nitrate solution. So first thing I'm going to do, I'm going to take this and move my decimal back 3 places, 0.208 liters, because if I'm going to be dealing with molarity, my volume has to be in liters. So I have my volume and I have my molarity. So just like we talked about in the little formula above, my first step would be I'm going to take my volume and I'm going to multiply it by my molarity. And when I do that, then I get how many moles I have. So I have 0.0208 moles of silver nitrate. Okay, and once again, that's just those 2 little formulas that we had right above this problem. That's where I'm getting that from. The first one, volume in liters times molarity equals moles of solute. So now if I know I have 0.0208 moles of silver nitrate, I'm really interested in grams of silver, then I can use my mole to mole ratio to get to silver. So looking at my balanced equation, it's a 2 to 2. So I have 2 moles of silver nitrate for every 2 moles of silver. So that leaves me with moles of silver. I want to get to grams, so the last step I would use would be the molar mass, which is 107.81 grams per 1 mole, and that's the molar mass of silver. Moles of silver nitrate cancel, moles of silver. I'm just left with grams of silver, so I'm going to multiply across and divide by 2. 3 sig figs, so my answer ends up being 1.12 grams of silver. If you don't like this way of figuring out how many moles you have, because you got to have how many moles, because that's the only way you can get to this mole to mole ratio and get from your known to your unknown. You could also do like we did in class. Remember we said there 0.100 molar. I don't know how many moles, but I do know that I have 0.208 liters. Bring that up, multiply, and you end up with the same thing. X is equal to 0.0208 moles, like we did. And then once again, that will start your problem. All right, let's look at one more. All right, this one I don't have a nice balance equation. So it says, what volume of copper nitrate will be formed? So that has to be my product. By the reaction of excess copper and silver nitrate. So this is a single replacement reaction where the copper is going to kick out the silver and become part of the compound. So that means I'm going to have some silver also left over here. Excess, so that tells me it's not a limiting reactant problem. So the last thing I need to do is a little bit of balancing. I think that gets everything balanced. So what volume of 3.5 molar copper nitrate will be formed by the reaction of excess copper, so I don't have to worry about copper, and 45 mils of silver nitrate? All right, once again, I'm going to change this to 0.0450 liters because I have to have it in liters. So I have the volume and the molarity of my silver nitrate. So once again, I can use the same little equation from up above these problems. I can take how many liters I have and multiply it by the molarity. And that gives me that I have 0.234 moles of silver nitrate. All right, I've gotten it into moles, and I needed to do that because I have to get from silver nitrate to copper nitrate. So now this becomes my given, 0.234 moles silver nitrate. For every 2 moles of silver nitrate, I have 1 mole of copper nitrate. So that means that I have 0.117, whoops, let's try that again. 0.117 moles of copper nitrate. But I want what volume I have, and I know the strength of that. So I'm going to say 3.5 molar is equal to, in this case, now I know the numerator, 0.117 moles, and X is on the bottom. So I multiply that, I get 3.5 M, 3.5X, because my X came up, is equal to 0.117. Divide each side by 3, and I get, by 3.5, 0.0334 liters. I got that by taking my 0.117 and divided it by 3.5. That's still 3 sig figs. So that's how many liters, or if I wanted to put it milliliters, 1, 2, 3, so 33.4 milliliters, still in 3 sig figs. So those are some pretty good problems. Like I said, we're not going to have a separate quiz on them. Probably will see at least one of those on your tests. So I would work through those. They're going to be similar to one of the two that you see there. All right, that's everything we need to get caught up on, and see you in class.